Right. So for about 10 years now, since 2010, actually, I've been doing yearly presentations on integrated circuit design at NTNU, and sort of going through the details of the circuit components and how do you make, how do you draw a transistor, how do you make a schematic, and all that stuff. And since I have then basically 10 presentations on virtually the same topic, I decided to sort of pick the best parts from each one of them and then just record some of the comments. Okay, so this is retro flashback to the previous presentations. Now, if you want to look at the originals, you can find those on my website. Anyway, it all started back in 1947. This was at Bell Labs, and you have, let's see, Shockley, Bardeen, and one other guy. Let's check. That doesn't work. Okay, let's do it like this now. Yeah. So, December 1947, Bardeen, Brattain, and Shockley. And this is sort of the first attempt and the first realization of a transistor. It was huge. It was not a CMOS. I don't really know what it was. I think it was a bipolar device. But it started a revolution, and one that's still going today. And it formed the basis of all electronics that we find today. So the second sort of innovation was being able to put multiple transistors on the same chip. This is the first one. So this was done by Jack Kilby back in at TI, I believe, Texas Instruments. Yep, he got the Nobel Prize for that, and that's a big thing because 1 was hard, 2 was harder, but then doing 4 is not that hard, or 5, or 10, or 32, or billion. And then if we scroll a bit forward in time, you have FPGAs. This is this is 6 years old, so there's probably something newer today. But basically, you have billions in transistors. But at this point, when you have billions, you start running into problems with how do you actually produce enough of them at high enough yield? And what ended up happening was that it wasn't economical to try and do it on a single chip. It was actually better to try and do multiple chips. So in this case, this is actually 4 28 nanometer chips on top of a 65 nanometer interposer, so basically just metal layers or interconnections, on top of I believe this is a bold red array package with space around here, probably for, I would assume, decaps. And that sort of was the state of the art. I would assume today, I haven't really looked, but you can find probably chips with more than this. Anyway, couple of things, couple of words. IC, integrated circuit, basically wherever you put multiple things, multiple circuit components on the same chip, like transistors, resistors, inductors, diodes. MOS, metal oxide semiconductor, basically just a stack of having metal and then oxide and then the semiconductor for the gate, I believe. And then field effect transistor, that you're able to pull charges or change the charge distribution underneath an oxide depending on the field. And then we have NMOS and PMOS. This is interesting. N-type MOS enhancement MOS. Okay, that seems redundant. Anyway, I'm not going to fix that. Right. When it comes to electronics, it is important to realize that although it may appear that the progress is extremely quick, it is actually relatively slow. So the fundamental principles of a bipolar transistor was known to Shockley, Brattain, and Bardeen back in 1947, which is now 70 years ago, more than 70 years ago. And if you could talk to them today, I don't know if they're alive, you would discover that they pretty much know how the electronics, when it comes to bipolars, works today also, because the physics hasn't changed. So when you decide what to focus on within electronics, you should take a look inside your own personality and figure out what is it really that you want to work on, and how fast do you need feedback? How fast do you need to see what you've made? How fast do you need to get recognition for the work that you've done? Because if you choose to work on, for example, a new type of transistor, maybe it's a nanotube tunneling FET or something like that, then it might take decades from your invention or the work that you do until you see something in the market, until you see something that's actually used by other people. Now, if you go the other end, if you do software design or embedded software, then you can go from your code compiling and everything being tested and perfectly okay to rolling out all across the world in virtually no time, sort of days to months. And you can get instant gratification that it's going to work. Now, if you move down here and do move down to making integrated circuits like this is actually a relatively old Nordic chip called NRF 8001. Let's see, I didn't work on, I was actually started in Nordic when this was made, but I don't have any analog designs on this. I do have a patent on a circuit inside in this though, but I just made the plan, somebody else did the design. But if you want to do things like that, then it takes time. It takes time from the work that you do to the production is done to the qualification, which maybe takes, I don't know, 6 months to a year, to getting the customer design wins, to actually seeing the component in the market will take years. And you have to be okay with that. You have to be okay that you won't get sort of instant feedback. So you have to choose, I think, based on what you want to do, or based on what you need as a personnel, or based on your personality, how do you want to position yourself? There is also an option to completely disregard or ignore what I'm saying here and find a new way to make stuff. Because it's really how we make stuff and how long it takes to get to the market that determines this time axis. Just because I say something doesn't mean it's going to be true forever. It's true right now, but you can change that. So let me walk you through how an integrated circuit is made. This is just an example from a company I work for. Let's see, it's generally how we do it today also. So if we start over here at the beginning, we do analog schematics and simulation, which is basically having a model, a mathematical model of the chip that we're going to make, testing that in the computer, and then hopefully that will work as it does when we get it back and measure it. And the same for digital. We code and then we ship it, and then hopefully it works. Because all models are wrong, but some are useful. And then we actually make the blueprint, or the layout as we call it, that serve as the recipe for how the manufacturing can be done. And after we send that to the factory, which is TSMC in Taiwan, They generate what's called the masks, and we have front-end process. So that's where you add the circuit elements. And then you have the back-end process where you add sort of the interconnections, metal layers, and so on. And then the final step is actually taking the silicon and putting it in a plastic mold, and then putting some pins on it, and then testing it every single circuit. And then you send it to customers, for example, keyboard and mouse customer, and they will integrate the chip, put it on their PCB, do their testing, and then at some point you can go and buy a wireless mouse. But how do we get there? So let's start at the beginning. What are the circuit elements in integrated circuits? The most important one is the transistor. Most transistors on integrated circuits are this type of complementary metal oxide semiconductor transistors. We still call them CMOS. It's not really CMOS anymore. Not necessarily metal. Well, I don't know, hafnium. I don't know if that's a metal actually. But it still has the sort of basic principle of 3 terminals. You have a gate, you have a source, and you have a drain. Basic principle is that let's assume source is 0. You connect that to ground. And then let's assume you increase the voltage on the gate. At some point, the current will start to flow from drain to source. As you increase the gate voltage more, the current increases. Now, these equations, that's sort of the simple thing here. The most simple thing is sort of to say, well, above a certain gate source voltage, then the current is high, and below it's low. That's the most simple method way to say it. That is sort of true. It is a model, but it's not correct. More correct is maybe to say that the current is actually proportional to the gate source voltage minus this magic threshold squared, which is true for a certain region and if the drain voltage is high enough. So in the end, the model that we use for CMOS transistors is usually something called the Berkeley BSIM. I think it stands for the Berkeley Simulation Model. Doesn't sound right now. It probably stands for something else. Google BSIM and you find what the abbreviation is for. But that is a function that gives you the drain current based on a bunch of different parameters. And these are the stuff you need to put in to this model to get the code, the program, to calculate the drain current. And we can recognize some of these parameters, right? So you have the effective oxide thickness is 1.8 nanometer. The zero threshold, or VTH0, is 0.25 volts. And the mobility is 0.032. And, well, I don't remember what the unit for mobility is right now, but some sort of thing proportional to meters and speed, I guess. You can look that up. And then you have other things like from the effective oxide, you can actually calculate directly the oxide capacitance and the width and length and so on. And that can give you a current. Now, if you go in and actually look at the BSIM 4.7 table of contents, so BSIM 4.7 we used back in bulk CMOS, for example, 65 nanometer or 55. You could use BSIM 4.7. Today, if you're using an FD-SOI process, it's a different BSIM model, but some of the parameters or some of the chapters will be similar. So you can go in here and you can see every single sort of effect that is modeled in a transistor. For example, let's see, short channel and dibble, so drain-induced barrier lowering. What is that? How is it modeled? Channel length modulation, which gives you the output resistance of or part of the output resistance of a transistor. How's that modeled? So all the different effects that we know of in transistors will be modeled in these mathematical equations. But as I said, this is a prediction of how the transistor is going to work. And it's based on our understanding today of how it works. Now that understanding is pretty good. So that means that when you simulate something or where you do the mathematical computation in the computer, you can be reasonably sure that it'll behave similarly when it comes back from production. But it doesn't always. And I have encountered that a few times where it does not behave as the model. Actually, a couple of times, particularly for noise, because you see here, noise modeling, chapter 10. Maybe you can't see it, maybe it's so small, but it says here flicker noise models, channel thermal noise, other noise sources modeled. Now, let me go to that link. Hopefully that still works. Ah, crap. Oh well. BSIM4, let's see, BSIM4. Okay. So let's see. Let's see. There we go, noise modeling. Okay, now let me make that a bit smaller. So we have flicker noise, and this is how the flicker noise is modeled. We recognize coefficients and 1 over the effective frequency. Slightly more complicated stuff. Channel thermal noise, so we can see how that's modeled in some sort of 4KT something. And let's see other noise sources. That's what I'm most, yeah, here we go. Thermal noise due to substrate, gate electrode, source rate, shot noise due to various gate tunneling components is modeled via LSFL. Right, but at this point, one interesting thing still is that it does not accurately predict what's called generation recombination noise or popcorn noise or telegraph noise. And that's actually something I've seen multiple times in nanoscale technologies where the circuit comes back and it behaves in a manner that does not fit with the noise measurements or the noise simulations that we do. It's simply completely different. And this is usually due to things like generation recombination noise and the fact that it is not in the SPICE model. So you actually need to know a bit about the physics and then basically guess what's going to improve and cross your fingers and test. Okay, let's see, let's get back to the presentation. Now, in integrated circuits, we also have other components. One of them is very useful, and that is some polyresistors, basically a short, thin metal, or not metal, polysilicon. So yeah, it's silicon, but it's not a single crystalline silicon. It's is it poly? I don't remember what the exact word, but we call it polysilicon. Now you can have that with silicide or without silicide. So basically with and without kind of metal doping on the top. And that can give you resistances. Now, the bad thing about these resistances is that the absolute value will change from, well, plus minus 20% maybe for different chips. So that's horrible. It's horrible for sort of compared to sort of discrete resistors that you can buy. But what's really good is that if you place two next to each other, the ratio between them will be extremely precise if you do the drawing correctly. So that means that you can get very precise ratios. So I can actually, with a simple resistor ladder like this, so if I have 1 volt here, I can actually ensure that you have 0.8 plus minus 0.1% and 0.2 plus minus 0.1%. Now, if this voltage changes, go from 1.1 to 1.2, then of course these will change. But the relation between them, or the division between them, will be extremely accurate. And that's a very, very nice feature of integrated resistors. Horrible absolute accuracy, extremely good relative accuracy. Capacitors in integrated circuits are usually either parallel plates. We used to use them in the olden days. So you had a metal and you have an insulator and they have a metal on top. These days, it's mostly sort of finger structures. So you do multiple layers of metals called metal oxide metal capacitors, and then they're pretty easy to generate, and you can also get relatively accurate precision between them on the order of maybe between 0.1 and 1% matching, depending on the size, because the accuracy or the how well they match between each other will depend on the size. Now, capacitors are very, very useful. We use them a lot to filter things. So if you have a noisy supply, like the red one here, and you want to generate something that's less noisy, well, you just put a resistor in series and then a capacitor. It's not perfect for when you're drawing current and maybe you're losing some power due to IR drop and things like that, but we do this. It's actually done inside circuits because it is very effective. And well, capacitor is also quite often used and together with its counterpart, the inductance. Now, capacitors can be very small. So you have a very large sort of capacitance ratio per square micrometer, maybe even up to, let's say, 10 femtofarad per micrometer. You could get sort of if you use a gate oxide on a transistor. Maybe if you use sort of a metal oxide metal, it's more like, I don't know, 5 or 6 or something like that. 6 femtofarads per micrometer squared. Yeah, something like that. But then inductors, they become very large. So at high frequency, at 60 gigahertz, you can get them small, right? Because the size, actually, well, the inductance depends on the frequency. Well, we can see, well, yeah, the inductance depend on the frequency. And how large do you have to have them? But they are unrivaled when it comes to generating clean sinusoids. So for example, put an inductor together with a capacitor together with some sort of active element to kick at the resonance frequency, and you have a very clean sinusoid clock generation. So that's pretty much used in all radio circuits where you have some sort of voltage controlled or digitally controlled oscillator, especially for the gigahertz range. So radios, you will always see these inductors on chip, and they're quite large. So we try not to use too many of them. But the parasitic inductors, so every single metal wire you put down on the chip will have an inductance. So for example, yes, you can draw amperes of current into a integrated circuit, but you need to think about the nanohenry inductance that's in the bond wire, the wire that goes from the chip to the package. And if you don't, you might actually destroy your circuit, because if you're pulsing that amp current, it can ring like crazy and actually cause it to be damaged. And I've seen that. Right, so the message for this part is it is not practical to sit down with a pen and paper and try to calculate how transistors are going to work. That's not the same as saying you don't need to learn how transistors work because you can use a computer. It's actually sort of the opposite. Even though you can use the computer to tell you what sort of rough drain current you have in a transistor, you need to know what's going on, because the model or the simulator or the calculation can be wrong, and then you need your intuition. You need to understand sort of how does the transistor work and what's the range of expected answer, right? So maybe you can, based on your sort of knowledge of how the transistor works, you will know whether the current should be 1 nanoamp or 1 microamp, sort of 3 orders of magnitude. You will know that based on just how that should work. So if the simulator tells you then it's running at 1 amp or 1 picoamp, then you will know that is wrong. So even though it's not practical to do hand calculation, you need to have a grasp of the physics. You need to understand the physics to be able to be an effective analog designer. Okay. I'm going to do this in a separate video. This is long enough already. So if you want to continue learning, then you should find also the other videos here. Bye.